Okay, so we have looked at the concept of a rank, and we have seen two different ways in which we could think of the rank, right? So one was, of course, using row reduction, which is perhaps the most foolproof way of getting to the rank of a matrix. You do a series of transformations and recast your matrix into a form where the bottom few rows, if there are any zero rows in the matrix, they are all pushed systematically to the bottom few rows, and then you count the number of rows which are non-zero, and that's the rank of a matrix, right? And then we saw that there's another way of computing the rank of a matrix, which was to look at all determinants of all square submatrices, right, of a given matrix, and find out the largest sized matrix which has a non-zero determinant, and that would be the rank of the matrix. Now there's a third way of thinking of the rank of a matrix, and this connects to the notion of linear dependence and linear independence, which we introduced many lectures ago. So I'm going to talk about this third approach in this lecture. Okay, so the idea is just look at any matrix. I have taken a 2 by 3, 2 rows and 3 columns matrix as an example. So the rank of this matrix is really the number of independent rows, right? So there are 2 rows, u1 and u2, right? We can use our Brown notation to represent these rows, right? So there are 2 row vectors, u1 and u2, and we immediately see that in fact u2 is 2 times u1. So in fact u2 and u1 are not linearly independent. There is only one, although you have 2 vectors, there is only one linearly independent vector. So the number of linearly independent rows of this matrix is the rank of this matrix, right? So the rank of this matrix is 1 because there's only one linearly independent row, and you can check this, right? Use some other method to row reduction, which will essentially come down to this, the fact that there's only one linearly independent vector, right? When you do these row operations, really underlying these row operations is also the property of the linear independence is hidden there, but it was not explicitly stated there, right? So it's just another perspective that we are giving you here. And so one very interesting and somewhat non-trivial aspect of matrices is the fact that you could also have thought of these in terms of the columns, right? You can ask yourself how many columns, there are these 3 vectors now. It's a 3 column matrix. So there are 3 vectors, v1, v2 and v3, 1, 2, 2, 4 and 3, 6. So you can ask how many linearly independent column vectors are there in this matrix, and it turns out that the answer is going to be 1, because we have already seen that there is only one linearly independent row in this matrix. And so it's a theorem really that for any matrix, the number of linearly independent rows has got to be equal to the number of linearly independent columns. And so in some discussions you might see this as defined as the row rank and the column rank, and then there's a theorem which shows that the row rank is equal to the column rank, and therefore there's no need to call it a row rank or column rank. You might as well just call it the rank of the matrix, right? So this is it's a non-trivial result, but it's for our purposes we'll use it like a rule, right? I mean, we are not going into some rigorous statement and proof type of approach is not the philosophy of this course. So anyway, so we will just it's important to be aware of this result, that the rank of a matrix is not just something that you obtain from row reduction, but it's also the number of linearly independent rows, or equivalently the number of linearly independent columns, right? So this is the general rule. For any matrix, the number of linearly independent rows is equal to the number of linearly independent columns, and both of these are equal to the rank of the matrix, right? So this is the rule which I would like you to verify, right? Look at all the different examples which you have already considered. Or make up your own matrices, 2 by 3s, 3 by 4s, simple matrices, not too large, and check for yourself that indeed, the number of linearly independent rows is going to be equal to the number of linearly independent columns, and each of them is going to be equal to the rank of the matrix as you would obtain either from the determinant approach or from the row reduction approach. Right? That's all for this lecture. Thank you.